Hello all, welcome back to the channel and welcome to the course on integral calculus. Recall in the last lecture we have seen about the topic integration by parts and have tried to understand the concept that how do we integrate by the integration rule of UV rule or say the Eilert rule, right? So in this lecture we are going to see about the integration of rational functions. So there are various methods to understand the integration of rational functions, but let us first understand that what are the rational functions. So if I say that we have a function called px divided by qx where qx is not equal to 0, then this function is known as the rational functions as the rational number, right? So the function formed by the rational number are known as rational function. Now we'll be discussing about the method of integration of rational functions. So there are various methods, but let us understand the method of partial fraction, which is most commonly used for the integration of rational functions. So method of partial fraction. The method of partial fraction involves the concept of making the fraction partial. So what is exactly mean by making the function partial? Let us see now. So suppose we have the integrals of the type px divided by qx, right? Now first of all we need to check the degree of px and qx. So if first of all the first step is to check the degree of px and qx, right? Or let it be say gx. So here it is gx, right? So now second step, if the degree of px is greater than degree of gx, then simply divide divide px by gx, right? We have to divide the px by gx if the degree is greater than px is greater than gx. So if the degree of the px is greater than degree of the gx, then we have to divide until the degree is less, until the degree is less, until the degree become less, then we have to divide it and make the form px upon gx as rx plus fx upon gx. Denominator should remain same, but the numerator becomes changed according to the value, and the remainder should be obtained, right? So where fx has degree less than gx, right? So for applying the partial fraction, it is very much important that we first divide the polynomial px upon gx, divide the polynomials and such that the degree of px should be less than degree of gx, and if it is greater than the gx degree, the degree of px, the numerator degree, then must be obtained the form as rx upon fx upon gx, rx plus fx upon gx, such that degree of fx is less than degree of gx. Now if the degree becomes less, then we have the following conditions, the different cases. So let us study the cases one by one. So it may happen that the form which the linear factors, basically the factors when dividing the fx by gx, so the gx factors basically into different cases. So one of the case is when it contains non-repeated linear factor, non-repeated linear factor. Then that is, like if I say the gx can be written as x minus alpha 1 times x minus alpha 2, it is not repeating, x minus alpha 3, and so on, x minus alpha n, non-repeating, and it is the linear, not in the form of a quadratic or biquadratic form. Then in such a case we write fx upon gx as, so write fx upon gx as what form? it is can be written as a1 upon x minus alpha 1, right? Here it is fx divided by gx plus a2 upon x minus alpha 2 plus a3 upon x minus alpha 3, and so on an upon x minus alpha n. So here just observe that we have written in the form of a partial fractions, and we are the motto is to find out the a1, a2, a3 up to an terms by comparing the coefficient of the denominator and the left hand side, right, and taking the LCM, right? So if both the sides we take the LCM, then we can easily find out the value of a1, a2 and up to an. So let us now do some problem related to it, right? So let us see, evaluate integration x upon x minus 2 times x minus 3 dx, right? So first of all, try to compare it with the px upon gx form. So we have to check whether the degree of px, that is x, degree of x, it should be what, and the degree of x minus 2 into x minus 3. So it is clearly seen that degree of x minus 2 and x minus 3 is greater than degree of x. So degree of x is less than degree of gx. So we can directly apply SC. If the fx is less than degree of gx, then we can see, and here also it is a linear factor. So x minus 2 and x minus 3 are the linear factors we have seen in the denominator. So we have to just try to write it as, so x upon x minus 2 into x minus 3 can be written as a upon x minus 2 plus b upon x minus 3. Now we have to find the values of a and b. So putting, so first of all let us take the LCM. So if LCM is to be taken, then it is a into x minus 3 plus b into x minus 2 divided by x minus 2 into x minus 3, and here it is x. So taking the numerator part, we have x is equals to a times x minus 3 plus b times x minus 2, right? So just try to put it as 3, right? So if we take putting x equal to 2, putting x equal to 2, what we got? Say in the left hand side 2 equals a times 2 minus 3 plus b times 2 minus 2, which is 0. So that is 2 equal to a times minus 1. So a equals to minus 2. So we have got the value as a equal to minus 2. Similarly, in the next step, putting x equal to 3. So we got 3 is equal to a into x minus 2 plus b into x minus 3, right? Oh, sorry, it is a into x minus 3 times x minus 2, putting x equal to 3. 3 equals to a into 3 minus 3 plus b into 3 minus 2. So that is how we got b equals to 3, the second equation. So we have got the values of a and b. Now simply write a upon x minus 2 plus b upon x minus 3, right? So now this px upon gx can be written as this. A value is minus 2 upon x minus 2 plus 3 upon x minus 3, right? Now make the integration. So integration minus 2 upon x minus 2 dx plus integration 3 upon x minus 3 dx. Taking the constant out of the sign of the integration, we have 1 upon x minus 2 dx plus 3 times 1 upon x minus 3 dx, right? So putting x minus 2 as t and x minus 3 as u, we got the different integration, and putting by the substitution method, we got to know that it is log of x minus 2 plus 3 times log of x minus 3, right, plus ka c. Okay, so it is, if we simplify the log expression, then we have the log a log b is log a power b form. So by that property, we have log of x minus 2 to the power minus 2 plus log of x minus 3 to the power 3. Now simply it is ln of x minus 3 cube divided by x minus 2 square plus c, right? So this is the final answer we got to know about the case of partial fractions when the factors are linear in advance of the denominator, right? So in this way we have solved the problem. Now let's move forward to the case 2, right? So case 2, when the factors are repeated as well as non-repeated, that is, suppose, so I will write when the factors are repeated or as well as non-repeated, right, and in form of linear factors, right? So then it is the case where the denominator gx could be written as x minus alpha 1 square into x minus alpha 2 into x minus alpha 3 and so on x minus alpha n, right? So in this way, if we got to know that the factors are repeated as well as non-repeated linear factors, then we can express fx upon gx as, simply now make a note of it, then it is fx upon gx can be written as a1 upon x minus alpha 1 plus a2 upon x minus alpha 2 square plus a3 upon x minus alpha 3, right, and so on an upon x minus alpha n, right? In this way we can linear factor, we can write it as the partial fraction form as this. So as the name suggests, students, it is the concept of partial fractions. So we are making the fractions partially, right? In this module we are making the fractions partially and try to write it as, because when we apply and take the LCM, then it becomes the same as the original fraction, right? So we have the authority to write it as this partial fraction form, right? Again, this a1, a2, a3 up to an can be find out by the concept of taking the LCM and comparing the coefficients of the denominator and numerator, both the sides, right? So for this, let us take an example to understand it much better, right? So the example is evaluate integration 3x minus 2 divided by x plus 1 square into x plus 3 dx, right? Okay, so now here you can say that it applies to the second case when we have studied that the factors are linear, repeated and linear, right, and non-repeated. So here we can write, suppose let px upon gx as 3x minus 2 divided by x plus 1 square times x plus 3, right? So here you can see that degree of px is less than degree of gx, right? So degree of gx is greater than degree of px. Therefore, we can write px upon gx as a1 upon x plus 1 plus a2 upon x plus 1 square plus a3 upon x plus 3, right? Okay, or to simplify it, we can write this is as a upon x plus 1 plus b upon x plus 1 square plus c upon x plus 3. So exactly the order doesn't matter much, students. We can write a, b, c anywhere according to our choice, but just make sure that the all the denominator terms are placed exactly same as we have learned in the cases concept, right? So here, can you see that now just try to compare. So here it is 3x minus 2 x plus 1 square times x plus 3. So taking the LCM, we got to know that it is a times x plus 1 times x plus 3 plus b times x plus 3 plus c times x plus 1 square, right? Simple enough. Okay, now here it is 3x minus 2, right? So now put, suppose let put x equal to minus 1, put x equal to minus 1, right? So if we put x equal to minus 1, then it is this a becomes 0 plus this b becomes minus 1 plus 3 plus c becomes 0, right? So for, and here it is minus 3 minus 2 minus 5. So minus 5 equals b times 2, right? So b equals minus 5 by 2. So we got the value for b, right? Similarly, let us try to find out the value for a and c similar pattern, right? So now let us see, put x equals minus 3. So putting x equals minus 3, get to know that b becomes 0 and also a becomes 0 plus b becomes 0 plus c times minus 2 square. So this is equal to minus 4. So c times minus 4 or plus 4 equals to minus 3. So c equals minus 3 by 4. Second equation. So c becomes minus, oh wait, putting c equals to minus 3. So that is becomes c equals to minus 3. So minus 3 plus 1, that is minus 2, that is 4. The 4 is correct, but here we have to put 3x minus 2. So 3 times minus 3 minus 2 minus 11. So it is minus 11 by 4, right? Similarly, put x equals, okay, so now not watching this method, right? So this method will not work. We have to directly equate the coefficient of x square and 0, right? So taking the coefficient of x square both the side. So here we got to know that 3x minus 2 has x square coefficient as 0, and here we have x square coefficient as a plus c, right? So we got to know that a plus c is 0. Then we have the value for c minus 11 by 4. So a plus minus 11 by 4 is 0. So a equals 11 by 4, right? So a equals 11 by 4 is the third equation. Now just put the values for the values a, b, c in the required integration part. So we have a upon x minus 1. So 11 by 4 upon x minus 1. 11 by 4 upon x minus 1 integration dx plus integration b value. So value of b is minus 5 by 2. So minus 5 by 2 1 upon x minus, so here we have x plus 1 whole square, x plus 1 whole square, x plus 1 and plus c, so minus 11 by 4 1 upon x plus 3 dx, right? So here after solving the integration part, basically what we got to know is the final answer as 11 upon 4 log of x plus 1 divided by x plus 3 plus 5 upon 2 times x plus 1 plus c, right? So 2 logs 11 by 4 and 11 by 4 combines, and we have the division rule because it is a minus sign there appropriately, and other than that part the b part has minus of x plus 1 square, so that becomes log of x plus 1, right? Because it is x plus 1 square, so it is 1 upon x square term. So basically 1 upon x square term is solved using the normal method, right? Minus 1 upon x basically, right? So minus minus plus and 5 by 2 divided by x plus 1, right? So here we have seen in this lecture the two cases for the integration partial fraction, right? So let me see if we can discuss more cases or not. Okay, so let's do one thing. Let us discuss the other three cases as well in this lecture. So now the case number 3. Case number 3 involves when the denominator contains non-repeated quadratic factor which cannot be factorized further. Remember that cannot be factorized further, the non-repeated quadratic factors, right? So suppose the gx can be written as suppose ax square plus bx plus c quadratic factors that cannot be factored further, right? Times x minus alpha 1 times x minus alpha 2 times x minus alpha n, right? So if it in such a case, then what we will be do, we will be writing fx upon gx as, write fx upon gx as fx upon gx equals a1x plus a2 divided by ax square plus bx plus c plus a3 upon x minus alpha 3, right? And so on an upon x minus alpha 1. So here make a correction, it is alpha 3 and alpha 4. So right, so here what we have done, if we have non-repeated not factorized further quadratic form, right? If we have the non-repeated quadratic factor which cannot be factorized further, then we can write fx upon gx, make sure the degree of fx should be less than degree of gx, and that should be written as a1x upon plus a2 divided by x square plus bx plus c plus a3 upon x minus alpha 3 up to so on an upon x minus alpha n, right? Again it could be seen that they should be compared with the coefficients of the numerator and denominator by taking the LCM on both the sides, right? Okay, so now we'll be solving the questions mixed, but before that let us discuss the case number 4. So case number 4 tells us that when the denominator contains contains a repeated, it should be a repeated quadratic factor. So in the previous case it was a non-repeated quadratic factor. Here it is a repeated quadratic factor which cannot be factorized further, which cannot be factorized further, right? So that is, suppose fx or gx, sorry, gx could be written as ax square plus bx plus c times square times x minus alpha 5, x minus alpha 6, and so on, x minus alpha n. Suppose we have non-repeated or repeated. Here it is repeated quadratic factor. In the previous case, case number 3, it was non-repeated quadratic factor. So here it is repeated case, repeated quadratic factor, and we have such a form of gx. Then in such a case we must write fx upon gx as a1x plus a2 divided by ax square plus bx plus c plus. So we have not done much other than that. We have not done much new to the this case, but we have just repeat the concept of the previous case. So we have, if one factor is quadratic, then it is a1x plus a2 divided by the factor, and we have just added another factor to it in the power 2. So we have just added another partial fraction a3x plus a4 divided by same ax square plus bx plus c, but here we have to make the square, right? And plus a5 upon x minus alpha 5, and so on an upon x minus alpha n, right? So here make sure that in the previous case number 2, as so much we have non-repeated factors we have seen, in the similar pattern we have to follow in the non-repeated quadratic factor as well, the same method, right? Okay, so now uh, corresponding to repeated linear factor in the denominator, make sure a sum of partial fraction of the type this form is taken. So suppose if I say that, if I say, make a note here, and if I say suppose it is corresponding to x minus a bar r in the denominator, right? So a sum of r partial fraction of the type is taken. So suppose we have power r, then we can take it as a1 upon x minus a plus a2 upon x minus a square plus, and so on, an ar upon x minus a raised to power r. So it should be kept in mind that whenever we are taking the non-repeated or repeated factors in the form of a r power in the denominator, then we must write it as a1 upon x minus a plus a2 upon x minus a square up to so on highest power ar upon x minus a raised to power r, and the rest terms which are non-repeated linear factors could be written in the further sequence as well, right? So make sure to apply date that, right? Now the case number 5 tells us that if the integrand contains only even powers of x, let's say contains only even power of x. So suppose it contains x square, x4 or x6 or x8, only even parts of x, right? Then just what we have to do is to put x square equals z in the integrand, right? X square equals to z in the integrand. Resolve the resulting rational expressions in z into partial fraction. So whatever will be left will be just resolved using partial fraction, right, of z. Then put z equal to x square again in partial fraction and then integrate both the sides. So we will be doing an example to understand it much better, right? So if this x square term should be if in the numerator, so I am talking about the case where we got to know and we get to see that x square is be available or present in the numerator side, then it should be manipulated, right? So it should be first changed to z, put it as z, then resolve the fraction as partial fractions, then again solving the values for a, b and c, then again put the value as x square and then directly solve the integration. So okay, so see the example. I will be demonstrating an example to see my case number 5, right? Other than that case, I hope you are very much now familiar. So let us try to evaluate this case. So it is 2x square upon x square plus 4 times x square plus 1 dx, right? So here you can see that if I talk about px upon gx, then this is 2x square upon x square plus 4 into x square plus 1, right? So now putting x square as z, we got to know that this is 2z upon x square plus 4 into x square plus 1. So again putting z in the denominator part as well. So z plus 4 into z plus 1, right? Okay. So now it is in the form. Now break it into the partial fraction. So basing it into partial fraction, it is a upon z plus 4 plus b upon z plus 1, right? Simple. Now therefore 2z will become a times z plus 1 plus b times z plus 4, right? So now just say put z equal to minus 1, so this is minus 2 equals 2b, so this implies b equals to minus 1. We have the value of b equals minus 1. Okay, sorry, just wait, it is 3, so b equals minus 2 by 3, right? And similarly put z equal to minus 4, then it is minus 8 equals a times minus 3, so a becomes 8 by 3, right? This is the value of a, right? So we have the values of a and b. Now what we have to do is to directly integrate. So 2x square upon x square plus 4 into x square plus 1 times 8 upon 3 times of x square plus 4 minus 2 upon 3 x square plus 1 dx, right? Now separate the integration. 8 by 3 integration 1 upon x square plus 4 minus 2 by 3 integration 1 upon x square plus 1 dx. So now it is tan inverse x. So 8 by 3 tan inverse x by 2 minus 2 by 3 tan inverse x plus ka c, right? So in this way we have solved the case number 5. Now it sometimes happens that if I give you a question, let us see. So what we'll be doing, if I will give you a question x square plus 1 divided by x4 plus 1, right? Or we have x square plus 1 divided by x4 plus x square plus 1, or we have integration dx upon x4 plus 1, right? So in all the three cases, what is most common? We have only the even power, right, of x. Not even a single odd power of x we have seen. We have to see. So in this case, what we have to do is to first divide the numerator and denominator by factor of x square, then I express the numerator as x plus minus 1 by x and denominator as a function of x plus minus 1 by x, right? So in this way we have to solve, right? So let us see one example for the same. Okay, so example, suppose we have the question as evaluate 2 dx divided by x4 plus 1. So it is of the form this one, right? So what we have to do? We have to divide first divide the numerator and denominator by x square, right? So here what we got it as, we have the I integration as dx upon x power 4 plus 1. This can be written as 2 times of 1 upon x square plus 1 upon x square dx, right? Simple enough. Now what we got to know? Now we have tried to express the numerator and denominator as the function of x plus minus x, right? Right, because we have to do the integration by substituting the value, right? So we have to apply the substitution method. That's why we are trying to evaluate the integration or putting it in the form of x plus 1 upon x or 1 plus 1 upon x form. So what we'll be doing is I am just adding and subtracting 1 plus 1 upon x square. So it is 1 plus 1 upon x square minus 1 minus 1 upon x square, right? Simple. So here, okay, right? So this way we are solving, right? And also because in the denominator we have x square plus 1 upon x square and dx, right? Integration, right? Because we have two times now. We have two times. So we have two times of this, right? So we have just used that part 1 upon x square as two times, right? Simple, right? And that is why we have able to uh, byparting it or expanding it along this way, right? So then we have the two separate integrations as 1 upon 1 plus x square upon x square plus 1 upon x square dx, right? Also, also we have plus 1 minus 1 upon x square, in between there is a minus sign, integration divided by x square plus 1 upon x square dx, right? Okay, now let's say in I1, so I have been naming the integrations as I1 and I2, okay? So now if it is okay, then in I1 assume x minus 1 upon x as t, right? So we got 1 minus 1 upon x square dx as dt, right? Simple. So now just see the elementary mathematics here. I have to write x square plus 1 upon x square in terms of x minus 1 upon x. So x minus 1 upon x whole square, that implies to be x square plus 1 upon x square plus 2, right? So that is, if I subtract t square minus 2, then we got to know the value of x square plus 1 upon x square. So that is way I1 becomes dt upon t square minus 2, right? Simple. And that it becomes integration 1 upon root t upon root t, sorry, 1 upon root 2 tan inverse t upon root 2 plus c, right? And here we have 1 upon root 2 tan inverse t's value is x plus 1 upon x divided by root 2 plus c. So we have the solution for I1. Similarly for I2, assume x plus 1 upon x as z. So therefore it is 1 minus 1 upon x square as dz, right? This is as dz dx, right? So therefore I2 would become 1 upon z square minus 2 dz, right? That is 1 upon 2 root 2. Now it's a square minus x square. So if it is a square minus x square, then we very well know that it is the integration of log of a x square a minus x upon a plus x, right? So it is 1 upon 2 root 2 log of 1 upon a basically. So 1 upon 2a, 1 upon 2a means 1 upon 2 root 2 log of z minus root 2 upon z plus root 2 plus c. And if I put the value of t, then it is 1 upon 2 root 2 log of z minus x plus 1 upon x. Oh, sorry, this should be not. Just wait. So it is x plus 1 upon x minus root 2 divided by x plus 1 upon x plus root 2 plus c, right? So for that part, if I combine I1 plus I2, then I get to know the I value, which is 1 by root 2 tan inverse x square minus 1 upon root 2x plus 1 upon 2 root 2 x square plus 1 minus root 2x divided by x square plus 1 plus root 2x plus c, right? So in this way, we have solved the concept for the even parts of x. Now suppose if the denominator cannot be factorized, then there are some different formulas we can see, right? So this will be all for this lecture. In the upcoming lecture, we are going to see more about partial fractions and try to solve some more problems, right? So thank you so much and have a nice day. So let us recall first what we have done so far. So we have seen the concept of partial fraction. We have seen how to make the partial fractions. If the degree of gx is less than degree of px, then we have to factor it, divide it, and if the degree of, until then we have become the degree of the numerator less than the degree of the denominator. Then we have case 1 where non-repeated linear factor, then we write it as partial fraction. Case 2 we have non-repeated, repeated as well as non-repeated linear factor, then we write it as this. And case 3 we have the quadratic form, and case 4 we have non-repeated repeated quadratic form, right? And now we have the even parts of x. So in total we have seen about 6 cases in total. So I hope you understand the concept well and try to apply it in your solving the problems which I have in the NCERT or in the different books for IIT-JEE as well as another competitive exams. So be prepared and try to solve more problems. Thank you so much and मिलते हैं अगले लेक्चर में. Till then keep watching and subscribe the channel. Thank you so much and have a nice day.